Today, I, Jyoti of class BSc Chemistry Honours first year, is here to read a chapter that is from Inorganic Chemistry, and this is chapter number 4, Ionic Solids from Modern's book, and the author of this book is Dr. S.P. Johar. So let's start from the introduction. Ionic solid contains an ionic bond which is formed between atoms by the complete transference of one or more valence electrons of one atom to the other atom. Therefore, in this type of bonding, one atom completes its octet, acquires noble gas configuration by losing the electrons, and other by gaining the electrons. The atom which loses the electrons acquires a positive charge, and the other which gains the electrons acquires a negative charge. These are two oppositely charged species ions that come closer due to electrostatic force of attraction and form an ionic bond. Since electrostatic attraction leads to decrease of potential energy and therefore the potential energy of the system becomes less than it was before the formation of ionic bond. The electrostatic force of attraction which holds the oppositely charged ions together is known as ionic bond or electrovalent bond. The compound containing ionic or electrovalent bond are called ionic compounds.
Now, first topic is formation of ionic bond. An ionic bond is formed when one or more electrons are completely transferred from one atom to another atom so that both the atoms acquire stable noble gas configurations. Let us illustrate the formation of ionic bond by considering the examples of sodium chloride. Sodium atoms whose electronic configuration is 1s2, 2s2, 2p6, 3s1 has only one electrons in the valence shell, and by losing this electron it can acquire stable electronic configuration of neon 1s2, 2s2, 2p6. On the other hand, chlorine atoms is 1s2, 2s2, 2p6, 3s2 and 3p5 has 7 electrons in its valence shell and needed only one electron to complete its octet. Thus, both the atoms can complete its octet if sodium atoms give one electron to chlorine atom. This tendency is responsible for bonding between sodium and chloride atoms. Therefore, sodium gives electrons and becomes positively charged Na positive ion, while chlorine takes up the electrons and become negatively charged Cl negative ions. These two ions are then held together by electrostatic force of attraction, which constitute an ionic bond. When an atoms combined by electron transfer, the number of electrons gained or lost must be equal so that the resulting compound on the whole is electrically natural. The number of electrons gained or lost by an atom in the formation of ionic bond is equal to its electrovalency. Atoms that readily lose electrons are said to be electropositive, while those who readily gain electrons are called electronegative. Let us consider another example of calcium chloride. Calcium Z equal to 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 has two valence electrons and can acquire the configuration of argon by losing these two electrons. In the formation of CaCl2, the two valence electrons of calcium are transferred to chlorine atoms Z equal to 17, that is 3s2 and 3p5, and all the ions thus formed when noble gas configurations. Schematically, the formation of CaCl2 may be represented as. Similarly, in the case of magnesium oxide, magnesium Z equal to 12, that is 1s2, 2s2, 2p6, 3s2 has 2 electrons in the outermost shell, and oxygen Z equal to 8, that is 1s2, 2s2, 2p4 has 6 electrons in the outermost shell. In the formation of magnesium oxide, both magnesium and oxygen attains the noble gas configurations by transfer of 2 electrons from magnesium to oxygen. The electrostatic force of attraction between Mg2 positive and O2 negative results in the formation of ionic compound, that is Mg2 positive and O2 negative. Schematically, this may be represented as. In this compound, the electrovalency of magnesium and oxygen is 2 positive and minus 2 negative respectively. Now, next topic is general characteristic of ionic solids. The ionic solids have the following characteristic properties. First, that is crystalline nature. In general, ionic compounds are crystalline in nature. X-ray studies of these compounds have shown that they do not exist in the molecular form but consist of ion of positive charged arranged in some definite geometric pattern. Each ion in the crystal is surrounded by a definite number of oppositely charged ions. The geometric arrangement of ions is different for different ionic substances. The mode of arrangement depends upon the size of ions and also on the respective charge on them. For example, in sodium chloride crystals, each sodium ion is surrounded by 6 chlorine ions. This arrangement is extended throughout the crystalline lattice. Now, second, high melting point and boiling point. In general, ionic compounds have high melting and boiling points and high heat of fusion and vaporization. It is because of the strong electrostatic force of attraction between the oppositely charged ions. Consequently, a large amount of energy is required to overcome inter-ionic attraction, which result in the increased melting and boiling points. The variations in the melting points as different ionic compounds are mainly due to first, charges on the ions, and second, ionic radii. The closer the ions in crystals, the larger will be electrostatic force of attraction and consequently higher will be the melting point. For example, in the case of sodium halides, the melting point decreases from NaF to NaI as the size of the ions increases from F negative to Cl negative. The force between the Na positive and halide ion become weak and consequently melting point decreases as given below. Now there are some salt with their melting points. First NaF with melting point 1270. Now second NaCl with 1073 melting point, NaBr with 1023 melting point, and NaI with melting point 924. In case the interionic distance is the almost same between the compounds, the melting point is determined by the charges of ions. For example, NaCl and BeO have almost similar internuclear distances, that is NaCl equal to 2.80 angstrom and BeO equal to 2.77 angstrom. The melting point of NaCl is 1073 Kelvin while the melting point of BeO is 2195 Kelvin. The higher melting point of BeO is due to stronger interionic attraction between doubly charged Be2 positive and O2 negative ions in comparison to attraction between singly charged Na positive and Cl negative ions. And third is hardness. Ionic compounds are hard and rigid. The hardness of ionic compound is due to the strong electrostatic force of attraction between two positively charged ions. Hardness of these compounds increases with the decrease in the interionic distances and increase in ionic charge for crystals with similar structures. For example, LiCl and SRO have similar structures and their interionic distances are also the same, 2.57 angstrom. SRO is harder than LiCl because of higher charge of ions in SRO and LiCl. Similarly, NaCl and CAS have similar structures and nearly the same interior ionic distances, but CAS is harder than NaCl because of high charge on ions. On the other hand, all the alkaline earth metal oxides MgO, CaO, SRO and BaO have similar structures and their ions are doubly charged, but their interionic distance increase in the group from MgO to BaO. Due to increase in their ionic distance, their hardness increases. Now, fourth point is brittleness. Ionic compounds are usually brittle, that is, they can be easily broken into pieces on applying stress. An ionic crystal consists of closely packed ions of opposite charges. When enough force is applied to ionic crystals, one layer of ions move across the next layer. As a result of ions of like charge come near to each other, this causes instability because of repulsion between similar ions and result into breakdown of the crystals. Fifth point is solubility of ionic compounds. Ionic solids are generally soluble in water and other polar solvents having dielectric constants. Since water has a high dielectric constant, it decreases the electrostatic force of attraction between the ions. As a result, the ions get separated from one another to give a solution. The ions in solution acquire a greater freedom of motion. Another favorable factor is that water acts as a dipole, having negative and positive ends. When an ionic compound is dissolved in the water, the positive end of the dipole interacts with the negative ion. while the negative end of the dipole interacts with the positive ion. Due to the strong interaction between the ions and the solvent, large amount of energy is released. This is known as hydration energy. The hydration energy released is greater than the crystal energy, which holds the ions. Consequently, the crystal lattice breaks and goes into the solution. Most of the organic solvents have low dielectric constant and are not highly polar. Hence, ionic solids are only slightly soluble in organic solvents. Sixth is conduction of electricity. The ionic solids consist of ions. They do not conduct electricity in solid state. The reason is that anions and cations, on account of electrostatic force, are held strongly at the particular position in crystal lattice and are not free to move. Hence, no current flows. However, as the temperature is raised, there is increase in kinetic energy of the ions when the substances are heated to high temperature so that they melt. The kinetic energy of the ions increases to such a large extent that they overcome the attractive force and become mobile and are thus able to conduct electricity in the molten state. Similarly, when ionic compounds are dissolved in water or some other solvent, the ions become free and therefore they conduct electricity in dissolved state also. Seventh is ionic reactions. Ionic compounds split up into oppositely charged ions when dissolved in water. The chemical reaction of ionic compounds are characteristics of the constituent ions and are known as ionic reactions. Such reactions occur almost instantaneously. Non-directional characters. The ionic bond is non-directional. In ionic compounds, each ion is surrounded by oppositely charged ions held together by electrostatic forces. These forces are uniformly disturbed all around the ions, that is, electric field is non-directional. The ionic bond is non-directional. Now, next topic is close packing of identical solid spheres. Before discussing the structure of some ionic compounds, it is worthwhile to understand the packing of constituent particles, that is, atoms, ions, or molecules in the crystals. In the formation of crystals, these particles get closely packed together. The closely packed arrangement in which maximum available space is occupied. The closer the packing, the greater is the stability of the crystals. In order to understand the packing of constituent particles of a crystal, let us consider the packing of hard spheres of equal size in three dimensions. If a number of spheres of equal size are put in a container and shaken, it is observed that they pack themselves in two common ways as shown in figure. In arrangement first, the spheres are packed in such a way that rows have been horizontal as well as vertical alignment. In this arrangement, the spheres are found to form squares. In arrangement 2, the spheres are packed in such a way that sphere is in every second row are placed in the depressions between the spheres of first row. In the third row, the spheres have vertical alignment with spheres in first row. A comparison of the two arrangements of spheres shows that arrangement 1, the spheres are lessly closed packed than in arrangement second. It has been calculated that in first arrangement only 52.4% of the available space is occupied by the spheres. The remaining 47.6% of the space is empty and is called void volume. In the second arrangement, 60.4% of the space is filled and 39.6% of the space is empty. Thus, the arrangement at second is more economical and it represents a close packing of spheres. It can be seen that in close pack arrangement 2, the centers of three nearest spheres are at the corners of equilateral triangle. Moreover, each sphere is in contact with six other similar spheres shown shaded in figure 4b. The number of nearest neighbors which has a given sphere is in contact is called the coordination number. Thus, the coordination number of each sphere is close pack arrangement is 6. Thus, the arrangement second represent close packing of sphere is in layer. We can build other layers above the first layer to extend the packing in three dimensions. Let us label the spheres in first layer as A. It is clear from figure 5a that there are two types of void hollows in the first layer. These are marked as A and B. All the hollows are equivalent, but the spheres of the second layer may be placed either on hollows which are marked A or on other set of hollows marked B. It may be noted that it is not possible to place spheres on both type of hollows. Thus, while building the second layer, only half hollows are occupied and half of the hollows remain unoccupied. Let us place the spheres on two hollow marked B to make the second layer, which may be labeled as B layer. The second layer is indicated by the dotted circles. When we come to packing of third layer, there are again two types of hollows available. One type of hollow marked A and are unoccupied hollows of first layer. The other type of hollows are hollow discussed in second layer marked C. Thus there are two alternatives to build the third layer as discussed below. First, the sphere of third layer may be placed on the hollows of the second layer, that is marked C. In this arrangement, each sphere of third layer lies directly above those in first layer. In other words, the third layer become identical to the first layer labeled A. This arrangement is continued indefinitely in the same sequence is represented A B A B A B A. This type of packing is known as hexagonal close packing and is abbreviated as HCP, that is shown in figure 6A. In this figure, the sphere of third layer are not shown because they are identical to a layer. For simplicity, it may be drawn as shown in figure 7. The second way to arrange spheres in third layer is to place them over the hollows marked A, unoccupied hollow of first layer. This gives rise to a new labeled as C, shown by dark spheres. This will give a different type of close pack arrangement. However, it can be shown that the spheres in the fourth layer will correspond with those in the first layer. This type of arrangement may be represented as ABC, ABCA. It is also known as cubic close packed arrangement and is abbreviated as CCP. This is shown in figure 8A and 8B. For simplicity, the CCP structure is represented in figure 8C. It is clear from figure 8 that there is a sphere at the center of each face of the cube. Therefore, this arrangement is also known as face-centered cubic arrangement, is abbreviated as FCC. It may be noted that both type of packing are equally economical, though these have different forms. In both these arrangements, 74% of available volume is occupied by the spheres. In addition to about two close pack arrangements, there is another arrangement of packing spheres known as body entered cubic arrangement. It is abbreviated as BCC. In this arrangement, the sphere in the first layer of close packing are slightly opened up. This is shown in figure 9. The sphere in second layer shown by dotted sphere in figure 9 are placed at the top of hollows in first layer. It is clear from the figure that each sphere in second layer is contact with four spheres of the first layer. In the third layer, spheres are placed exactly above the first layer. Therefore, in this arrangement, each sphere is in contact with 8 spheres, 4 in the layer below and 4 in the layer above it. This arrangement can be described as cubic arrangement in which there are 8 spheres at the corner of cube and 1 sphere is at the center or body of the cube. The structure may be shown in figure 9. In BCC arrangement, only 68% of the volume is occupied and therefore it is less economical than HCP and CCP arrangement. Next topic is interstitial sites in close pack arrangements. We have observed that even in close packing spheres, certain hollows are left vacant. These hollows holes or voids in the crystals are called interstitial sites. These sites are named depending upon the geometry in terms of positions of the atoms surrounding the holes. For example, in the close packed arrangement of sphere, the centers of three spheres lie at the vertices of an equilateral triangle. The empty space between these spheres is called triangular site. There are two important type of interstitial sites in crystals. These are first tetrahedral site and second is octahedral site. Now first tetrahedral site. This type of site is formed when a sphere is the second layer is placed above the three spheres touching the another in the first layer. This is shown in figure 10. The centers of the four spheres are disposed towards of the corners of a regular tetrahedron. It may be noted that shape of the hole is not tetrahedral, but the arrangement around the hole is tetrahedral. Now second is octahedral site. This type of site is formed at the center of six spheres. The center of each form a regular octahedron. This is shown in figure 11. From the figure it is clear that octahedral site is formed by two sets of equilateral triangle which point is opposite direction.
Now next topic is ionic structures. We have learned then that in the formation of crystals, the constituent particles, atom, ions or molecules get closely packed together. The closely packed arrangement is that in which maximum available space is occupied. The closer the packing, the greater is the stability of the crystal. All crystalline substances have definite orderly arrangement of their constituent particles in three dimensions. The regular arrangement of the constituent particles of a crystalline solid in three-dimensional space is called space lattice. If we carefully look at a space lattice, it is observed that we can select a smallest repeating pattern or motif which is repeated over and over again in the whole crystal lattice. The smallest repeating unit in space lattice, which when repeated over and over produce the complete lattice, is called unit cell. This smallest repeating pattern or unit cell represents the shape of the entire crystal. It must be remembered that while drawing the structure of ionic solids, we do not draw the complete crystal lattice but a unit cell. In the simple ionic compounds, generally two types of arrangements are possible. These are cubic close packed CCP arrangement and hexagonal close packed, that is HCP arrangement. The larger ion, that is anions, adopt these arrangements. The CCP arrangement, also known as FCC arrangement, can be obtained by placing atoms at all the corners of the cube, and at the center of each face there are six faces. This arrangement is also called ABC arrangement. There are 4 atoms per unit cell in this arrangement. The HCP arrangement is drawn by placing atoms at all the corners of the hexagonal faces and at their centers. One layer is made between these two identical layers. If we join opposite corners of a face, we can get 6 triangles, sides surrounded by 3 atoms. The second layer is formed by placing the atoms above alternative triangles. This arrangement is also called ABABA arrangement. The cation occupies the interstitial sites of these arrangements. As already learnt, there are two types of sites which are commonly occupied. These are octahedral sites and tetrahedral sites. There are two tetrahedral sites for each atom and one octahedral site for each atom. Let us visualize these sites in these arrangements. Location of interstitial sites in close packed arrangement. First is CCP arrangement. The octahedral sites in CCP arrangement are between the two anions. Obviously, these are at the center of every edge and in the body center. In this figure, only the octahedral sites of top face are shown by dark spheres and the hollow spheres represent anions. If we carefully see the CCP arrangement, we observe that it has 8 small cubes. Each cube has 4 anions at the alternate corners. The center of the small cube becomes the tetrahedral site. There are 8 small cubes and therefore there are 8 tetrahedral sites. Second is HCP arrangement. In HCP arrangement, the octahedral and tetrahedral sites are shown. We have learnt earlier that the second layer in HCP arrangement is made by placing atoms on the alternative triangles in the face. For example, B layer is formed by placing atoms above the triangle marked crosses. The octahedral sites correspond to the other triangles not marked by crosses in the figure. The tetrahedral sites are shown above and below each atom. For simplicity, only the tetrahedral sites above the bottom layer are shown filled. Now let us discuss some important structures of two types AB and AB2. In the structure of AB type, the two types of ions A positive and B negative have same coordination number, that is number of nearest neighbors. However, in these compounds of AB2 or A to B types, the two kinds of ions A positive and B negative have different coordination number which are in the ratio of 2:1 or 1:2 respectively. It may be noted that we consider close packed arrangement of ions, though the close packed arrangement may slightly expand in order to accommodate the opposite ions. As a result, the structure may be slightly open up structure, but the close packed structure is often a good starting point for the discussion of these structures. Now, structures of AB type ionic solids. Three commonly found AB type structures are sodium chloride, that is rock salt, Structure, zinc blende structure and cesium chloride structure. First is structure of sodium chloride NaCl. The unit cell of sodium chloride is shown in figure. In this structure, the sodium ions are represented by solid circles and chloride ions by hollow circles. The silent features of the structure are as follows. First, the chloride ions are arranged in CCP type arrangement. In this arrangement, the chloride ions are present at the corners of the cube and at the center of each face. As discussed earlier, this arrangement is also known as face-centered cubic FCC arrangement. Second, the sodium ions occupy all the octahedral sites. Thirdly, there is only one octahedral site per atom in a close packed lattice. Therefore, there will be one Na positive ion for every chloride ion. This means that the ratio of Na positive and Cl negative ions in this structure is 1:1. In other words, the stoichiometry is 1:1 in sodium chloride crystal. This stoichiometry can be understood by counting the number of Na positive and Cl negative ions which contribute to the unit cell as discussed below. Now figure shows that there are 8 chloride ions at the corners and 6 at the faces of unit cell. We can easily understand from the figure that each ion at the corners is shared between 8 unit cells and its contribution per unit cell is 1 by 8. Similarly, each ion on a face is shared by 2 unit cells so that its contribution per unit cell is 1 by 2. Therefore, 8 chloride ions at the corners is equals to 8 multiply 1 by 8, that is 1 chloride ion per unit cell. Then 6 chloride ions at the faces is equals to 6 multiply 1 by 2, that is equals to 3 chloride ions per unit cell. Total number of chloride ions in the unit cell is 1 plus 3, that is equals to 4. There are 12 Na positive ions on the edges and 1 inside the cell. It can be easily seen that each ion on the edge is shared by 4 unit cells and its contribution per unit cell is 1 by 4, while the ion at the body center contributes only to 1 unit cell. Therefore, 12 Na positive ions at the edges is equals to 12 multiply 1 by 4, that is equals to 3 Na positive ions per unit cell. 1 Na positive ion inside the cell, that is equals to 1 Na positive ion per unit cell. So total number of Na positive ions in the unit cell is 3 plus 1, that is equals to 4. Thus the stoichiometry of Na positive to Cl negative ions is 4:4, that is equals to 1:1. Fourth point is, in this structure, each Na positive ion is surrounded by 6 chloride ions which are disposed towards the corners of a regular octahedron. This has also been shown in the figure. Similarly, each chloride ion is surrounded by 6 sodium ions. Thus, the coordination number of Na positive ion as well as that of chloride ion is 6. This type of structure is adopted by most of the alkali metal halides, that is NH4Cl, then NH4Br, NH4I, AgF, AgCl, AgBr, etc. Second is structure of zinc sulfide. It has two types of structure known as zinc blende structure and Wurtzite structure. First is zinc blende structure, that is ZNS. The unit cell of zinc blende structure is shown in figure. In this structure, the zinc ions are represented by solid circles and the sulfide ions are represented by hollow circles. The salient features of this structure are as follows. First, the sulfide ions are in CCP type arrangement. This arrangement, the S2 negative ions are present at the corners of the cube and at the center of each face. The zinc ions occupy half of the tetrahedral sites. Thirdly, there are 2 tetrahedral sites per atom in a close packed lattice. This means that there are 2 tetrahedral sites available for every S2 negative ion. In this arrangement, only half of tetrahedral sites are occupied by Zn2 positive ions. Therefore, there is one Zn2 positive ion for every S2 negative ion. So, the stoichiometry of the compound is 1:1. Fourth, in this structure, each zinc ion is surrounded by 4 sulfide ions which are disposed towards the corners of a regular tetrahedron. Similarly, each S2 negative ion is surrounded by 4 Zn2 positive ions, which are also disposed towards the corners of a regular tetrahedron. The arrangement around one Zn2 positive ion and one S2 negative ion is also shown in figure. Thus, the cations and anions are present in equivalent positions, and the coordination in zinc blend is described as 4:4. This structure is also adopted by compounds such as ZNO, CuCl, CuBr, CuI, and BeS, etc. Second is Wurtzite structure. The unit cell for Wurtzite structure is shown in figure. In this structure, Zn2 positive ions are represented by solid circles and S2 negative ions are represented by hollow circles. The salient features of this structure are as follows. Firstly, the sulfide ions are arranged in a hexagonal closed packed, that is HCP arrangement. The zinc ions occupy half of the tetrahedral sides. In HCP arrangement, for each S2 negative ion, there are two tetrahedral sides, one above and one below it. In this figure, only tetrahedral sides above the S2 negative ions are shown filled. The tetrahedral sides below the S2 negative ions remain vacant. Thirdly, there are two tetrahedral sides per atom in the closed packed lattice. This means that there are two tetrahedral sites available for every S2 negative ion. Since only half of these are occupied by Zn2 positive ions, the stoichiometry of the compound is 1:1. Fourth, in this structure, each S2 negative ion is surrounded by 4 Zn2 positive ions, which are disposed towards the corners of a regular tetrahedron. Similarly, each Zn2 positive ion is surrounded by 4 S2 negative ions, which are also disposed towards the corner of a regular tetrahedron. The arrangement around one Zn2 positive ion and one S2 negative ion is shown in figure. Therefore, the coordination number of Zn2 positive and S2 negative ions in Wurtzite structure are 4:4. Other examples of this type of structure are ZNO, CDS, CASE, BeO, etc. The basic difference between zinc blende and Wurtzite structures. It will be noted that the basic difference between zinc blende and Wurtzite structure is that in the zinc blende structure, the sulfide ions are arranged in CCP type of packing, whereas in Wurtzite structure, they are arranged in HCP type of packing. The coordination number of Zn2 positive and S2 negative ions are 4:4 in both the cases. Now, third structure is of cesium chloride, that is CSCl. The unit cell of CSCl is shown in figure. In this structure, cesium ions are represented by solid circles, whereas chloride ions are represented by hollow circles. The salient features of cesium chloride structure are as follows. Firstly, the chloride ions are arranged in the simple cubic arrangement. In this arrangement, the chloride ions are present at all the corners of the cube. Secondly, the cesium ions occupy the cubic sides, that is, Cs positive ions are present at the body center of the cube. Thirdly, it is clear from the figure that there are 8 chloride ions at the corners of the cube. Each ion at the corner is shared between 8 unit cells and its contribution per unit cell is 1 by 8. Therefore, 8 chloride ions at the corners is equals to 8 multiply 1 by 8, that is 1 chloride ion per unit cell. There is also one cesium positive ion in the body center and its contribution per unit cell is 1. Thus, for Cs positive ion, there is one chloride ion so that the stoichiometry is 1:1. Fourth point, in this structure, each Cs positive ion is surrounded by 8 chloride ions which are disposed towards the corners of a cube. This is clear from figure. When the unit cell is extended as shown in figure, it becomes clear that each chloride ion is also surrounded by 8 Cs positive ions. Thus, both types of ions are in equivalent positions. Therefore, the coordination numbers of cesium positive and chloride negative ions are 8:8. Cesium chloride type of structure is adopted by CSBr, CSI, TLCl, TLBr, etc. Note: it may be noted that the structure is sometimes wrongly described as body-centered cubic, but this is a misnomer because the body-centered cubic structure is one which has the same atoms at the body center as well as at the corners. But in cesium chloride, the atoms at the corners are different than the atoms at the center. Now is the structure of AB type ionic solids. First is fluoride structure of CaF2. The unit cell of CaF2 is shown in figure. The calcium ions are represented by solid circles and fluoride ions are represented by hollow circles. The CaF2 structure may be described as follows. Firstly, the calcium ions are arranged in CCP arrangement. In this arrangement, Ca2 positive ions present at all the corners and at the center of each face of the cube. Secondly, the fluoride ions occupy all the tetrahedral side. Thirdly, there are two tetrahedral sides per atom in a closed packed lattice. This means that there are two tetrahedral sides for every Ca2 positive ion. Since F negative ions occupy all the tetrahedral sides, there will be two F negative ions for each Ca2 positive ion. Thus, the stoichiometry of the compound is 1:2. In this structure, each F negative ion is surrounded by four Ca2 positive ions which are disposed towards the regular tetrahedron. On the other hand, each Ca2 negative ion is surrounded by 8 F negative ions which are disposed towards the corner of a cube. Thus, the coordination number of Ca2 positive and F negative ions are 8:4. The structure is adopted by a large number of fluorides such as CuF2, BaF2, SrF2, PbF2, HgF2, etc.,